Okay, so today we start homogeneous functions and then their theorem. What is homogeneous function? Let me write down one expression, that is a0 x power n plus a1 x power n minus 1y plus a2 x power n minus 2y square, and up to, in the end, let it be an y power n. So then for each term the total degree is n. X power n, the degree is n. X power n minus 1 into y, n minus 1 plus 1 degree from y, again it is n. Similarly for the next term, this is n minus 2 plus 2. तो पूरा जो टोटल टर्म है उसकी डिग्री कितनी बन गई n. तो इस तरीके के एक्सप्रेशन में जब for every term the degree is n, such a function is called homogeneous function in x and y of degree n. So this is called homogeneous function of degree n. Now I may write down this expression as x power n कॉमन लीजिए, this will be a0 plus a1 y by x, right, plus a2 y divided by x square, and in the end it will be an y by x power n, right? So now here you see that this is a polynomial in y by x of degree n, right? So this can be written as x power n, a polynomial n, polynomial Pn in y by x, degree is n. So a homogeneous function can be written like this: the power of x is n multiplied by a polynomial Pn of y by x, degree is n. Is it okay?
Yes, sir.
So now this can be generalized now. A function of this type, x power n into f y by x, instead of polynomial I may generalize it x power n into f y upon x. This is a homogeneous function of degree n. The variables are 2, x and y. Is it okay?
Yes.
Right. So in this way, if I write down x power 4 10 y by x, this is nothing but a homogeneous function of degree 4 in x and y. Anything like this also. So let me write down x power 5 e power y by x. This is a function, homogeneous function, degree is 5. ठीक है, तो डिग्री कितनी होगी 5. Clear?
Yes.
Okay. So if I am having such type of functions, they are called homogeneous functions. Let me have another example. If I write down one expression like this, x power 1 by 4 plus y power 1 by 4 divided by x power 1 by 8 plus y power 1 by 8. There is a question whether this function is homogeneous or not. If it is homogeneous, what is the degree? So can you find out it? If I take x power 1 by 4 common for numerator, this can be written as x power 1 by 4, yes, 1 plus y upon x power 1 by 4 divided by, I take x power 1 by 8 common, so this will be x power 1 by 8, 1 plus y upon x power 1 by 8. This whole expression, this one can be written as a function of y divided by x, and upon simplification this will be x power 1 by 4 minus 1 by 8. 1 by 4 minus 1 by 8 will be equal to 1 by 8. So this is x power 1 by 8 f of y by x. So this is again a homogeneous function. The degree is 1 by 8. So is the topic of homogeneous functions clear? Right. Now I take Euler's theorem. Euler's theorem. Let u is equal to x power n f y by x be a homogeneous function of degree n in x and y, be a homogeneous function of degree n in x and y, then what is the statement of Euler's theorem? X del u over del x plus y del u over del y, this will be equal to nu. It means on the right hand side the function u will be there multiplied by n, that is the degree of the function, and on left hand side it is x del u over del x plus y del u over del y. This can be easily proven. Let me go for proof. What is here? U is equal to x power n f y upon x. I may put t is equal to y divided by x. So u will be equal to x power n f of t. Right? Now let me differentiate it first with respect to x and apply the chain rule. What will be del u by del x? Right? Product rule. The partial derivative x power n will be equal to n into x power n minus 1. X power n into x power n minus 1. And the function ft as it is plus, because the product rule is there, plus x power n derivative of ft now with respect to x. If I apply chain rule, this will be f dash t, derivative of f with respect to t, f dash t, and then derivative of t with respect to x, and of course partial. So into del t over del x. Is it clear? Now what is t? T is nothing but y by x. So del t over del x will be equal to, y is a constant, 1 upon x. इसलिए क्या करेंगे, दिस विल बिकम माइनस 1 अपॉन एक्स स्क्वायर, एक्स पावर माइनस 1 माइनस 1, एक्स पावर माइनस 1 माइनस 1, एक्स पावर माइनस 2, तो माइनस 1 अपॉन एक्स स्क्वायर. So this expression will be equal to n x power n minus 1 ft plus x power n into f dash t into minus y upon x square. So finally this will be n x power n minus 1 ft minus x power n minus 2 into y and into f dash t. Is it okay? This is the expression for del u by del x. So now what should I find? X del u over del x. So then x del u over del x will be equal to n x power n f t minus x power n minus 1 by f dash t. Now let me go for the partial derivative with respect to y. So del u over del y will be equal to x power n, this is constant, then ft, of course ft is a function of y because t is equal to y upon x. So the complete derivative f dash t into del t over del y. Now t is equal to y upon x, so del t upon del y will be equal to 1 by x. So this will be x power n f dash t into 1 upon x, and upon simplification this will be x power n minus 1 f dash t, and I need here y del u by del y. So the expression for y del u over del y, this will be now x power n minus 1 by f dash t, and we are almost done because upon addition x del u upon del x plus y del u upon del y, this term will be cancelled out, and what will remain there? N x power n into ft, and this x power n ft is equal to u. So the final result has arrived, that is x del u over del x plus y del u over del y is equal to n u, right? So I am skipping it. You can easily understand that final result will be x del u over del x plus y del u over del y is equal to n u. Clear to all of you? Fine? Right. Now this Euler's theorem can be extended to more variables. Number one, if u is a function, rather u is a homogeneous function, in right now I was having two variables x and y, independent variables. If there are more than two independent variables, let me say 3 x, y and z. So this is a homogeneous function with three independent variables x, y and z. Then Euler's theorem says in this case that x del u over del x plus y del u over del y plus z del u over this will be equal to n u. And the proof I am leaving to all of you. You can easily go in the similar fashion as we did for a 2 variables. Here, another result that we may derive. Of course, use a function, homogeneous function in the variables x and y, then x square del square u over del x square plus twice xy del square u over del x del y plus y square del square u over del y square. This will be equal to n into n minus 1 u. This is another result. I am leaving it again to all of you to complete this exercise. Clear? This can be done similar fashion. Make second variable with respect to x, make second variable with respect to y, make mixed derivative first with respect to y, then with respect to x. Is it clear? If it is not done, we can have in tutorial class, no problem, right?
Sir, 8 minutes, sir.
So now I move to a new topic, that is Jacobian. What is the term Jacobian? This is a new terminology. What is the meaning of Jacobian? Of course, the definition is not a tedious one. It's a very simple one. Let u and v be the two functions depending upon two independent variables x and y. Be two functions depending upon two independent variables x and y, that is u is equal to u of xy and v is equal to v of. Right? Now I am having two functions u and v depending upon x and y. Again, let x and y be functions of s and t. Let me say two parameters s and t. That is x depending upon st and y depending upon again st. Is it clear? So this such type of situations give us the rise of the definition of and the necessity of the definition of a Jacobian. Now what is that? First, the Jacobian of u and v with respect to x and y. The Jacobian of u and v with respect to x and y. This is nothing but a determinant of partial derivatives, that is del u over del x and del u over del y and del v over del x and del v over del y. This determinant is called Jacobian of u and v with respect to x and Clear? Definition clear? Now upon expansion, this will be equal to del u over del x into del v over del y and minus del u over del y into del v over. So this expression is called Jacobian of u and v with respect to x and y. Of course, I can have a opposite situation as well. Jacobian of xy with respect to u and v. What is this? Jacobian of xy with respect to u and v. This will be nothing but again del x over del u into del x over del v, right? And then del y over del u into del y over del v, right? Okay. So now again I am having x as a function of s and t and y as a function of s and t. Then I can have the Jacobian of x and y with respect to s and t. So Jacobian of x and y with respect to s and t. This will be is it okay? Jacobian of xy with respect to Jacobian with respect to s and t. So this will be again del x over del s and del x over del t and del y over del s and del y over del t. Now the chain rule, because earlier I told you in partial differentiation the situation whenever u and v were functions of x and y and x and y were the function of s and t. So that chain rule now can be expressed now in terms of a Jacobian. How is that? Just get the multiplication of Jacobian of uv with respect to x and y and then Jacobian of xy with respect to s and t, right? So now there will be the multiplication of two determinants and upon simplification you will get the expression that is Jacobian of uv with respect to s and t. What is here? Jacobian of uv with respect to x and y and then Jacobian of xy with respect to s and t. Finally the result will be Jacobian of uv with respect to s and t. You can get this expression upon the multiplication of two determinants. Is it clear? Should I do that exercise?
Yes.
Huh? Is that needed? I hope you can do. If it is not done, we can have in tutorial class. No problem. Done? Now, one important property of Jacobian. From here, using this rule, if I multiply the Jacobian of uv with respect to xy and then Jacobian of xy with respect to u and v. Just see here. In this way, Jacobian of uv with respect to x and y and then Jacobian of xy with respect to u and v. Using this rule, the result will be Jacobian of uv with respect to uv. The Jacobian of same variables u and v with respect to the same variables u and v. Now let me have the definition. Finally, this will be equal to del u over del u, del u over del v, and then del v over del u and del v over del v. Now the derivative of u with respect to u, this will be equal to 1, and the derivative of u with respect to v, because they are independent variables, the change of v will not affect the change of u, so the value of the derivative will be 0. So this will be equal to 1 0 and 0 1. The value of the determinant will be equal to 1. Is it clear?
Yes, sir.
Right?
Yes, sir.
So in this way, I will introduce the notion of Jacobian. Right? Given two functions of two variables, I can define the Jacobian. Is it clear?
Yes.
So where is it used? The definition of Jacobian is used whenever I am having two functions and then two independent variables. The situation can be extended if I am having three functions and three independent variables. I may have four functions and four independent variables. I may have five functions. I may have five independent variables. In every situation, the Jacobian can be defined. Is it okay? So let me have the case of three functions and three variables. If u, v and w are functions of x, y and z. Then Jacobian of u, v, w with respect to x, y and z. This will be again a determinant of order 3 by 3 of type 3 by 3. Earlier it was 2 by 2. So what will be? Del u over del x, del u over del y, del u over del z. Second row, del v over del x, del v over del y, del v over del z. Then del w over del x, del w over del y and del w over del z. So this is a 3 by 3 determinant, right?
Yes, sir.
So the value of this determinant will be called Jacobian of u, v, w and with respect to x and y. So this is okay. The previous results can be extended here. How? If u is a function of x, y, z, v is a function of x, y, z, w is a function of x, y, z, and now x is a function of s, t, r, y is a function of str, z is a function of str. Is it okay? So then I can write down that Jacobian of xyz, sorry, Jacobian of UVW with respect to xy and z multiplied by Jacobian of xyz with respect to str. This will be nothing but Jacobian of UVW with respect to st and r. Is it clear?
Yes, sir.
Similarly, Jacobian of UVW with respect to xyz and multiplied by Jacobian of xyz with respect to UVW. The value will be equal to. So the results can be extended to 3 functions and 3 variables, and similar type of definition, similar type of results can be extended to 4 functions, 4 independent variables, 5 functions, 5 independent variables, and so on. 6, 7, 8, 9, 10. Is it clear? So this is the notion of Jacobian. Now what are the applications of Jacobian for our case? That we shall study in the next class. Right? So we stop here.